All right. Hello, everyone. Today we will be figuring out what the structure is of this mysterious organic molecule. We have been given the molecular formula. It is C10H12O. So we'll first start by calculating the sites of unsaturation, and this is going to tell us the number of double bonds in the molecule. So we're going to take the number of carbons, which is 10, multiply by 2, add 2 to get 22. And that is the maximum number of hydrogens that could be on this molecule if it was fully saturated. So then we take that number, we subtract the actual number of hydrogens, which is 12, divide by 2, and we get 5 sites of unsaturation. So this is a lot of double bonds. So this is going to be my first hint that this molecule is going to have an aromatic ring somewhere in it. So now we can move to IR, the IR spectrum. There are a bunch of different peaks here, so let's just break this down a little bit. The first peak is pretty characteristic of any organic compound. We see a peak at about 3,000 or so. This is going to correspond to the sp3CH stretching. So this doesn't really tell us too much. However, our next peak is very characteristic. We have a very, very large peak at about 1700 or 1750 centimeters to the -1. And this is going to be a CO double bond. So we know from our molecular formula we have one oxygen atom, so we've accounted for it, which is great. Then moving on to kind of the 1300 to 1500 range, this is where we would normally see our sp3CH bending peaks. And we're seeing a lot of them. They're very narrow, as opposed to kind of being more condensed into fewer peaks. So this is actually characteristic of an aromatic ring. So that kind of confirms what we thought with the sites of unsaturation. So I've added that to this table here. And then finally, the other characteristic peak that I am seeing is we do have a pretty large peak at about 700 centimeters to the -1. So where this wave number is, this is going to be an out-of-plane bend peak, which again kind of corroborates the idea of having a lot of double bonds, having an aromatic ring, because when you have double bonds, that contributes to these out-of-plane bends. So what can we learn from our IR spectrum? Well, there's a couple of things. All of these peaks kind of corroborate the idea that there is an aromatic ring within the compound, but more importantly, we can see that we have a CO double bond, but what's equally as important is what we're not seeing. Obviously, we're not seeing any bonds related to nitrogen, but we're not seeing any bonds related to oxygen other than that CO double bond, so no OH, no CO single bonds. So what this tells us is that this molecule is either an aldehyde or a ketone. Um, to kind of distinguish between the two, we know that aldehydes have these two characteristic peaks at about 2800 and 2750 centimeters to the -1, and we're not seeing those peaks on our spectrum, so we can assume that this compound is a ketone that has an aromatic ring somewhere in it. So with that, we can move on to 13C NMR. So there's quite a few peaks here. So again, we'll just break that down, starting at the farthest downfield. So this is obviously very, very far downfield, and anything above 200 parts per million is going to be an aldehyde or a ketone. So that's great. That's just agreed with our IR spectrum. Even better, we then have these multiple peaks between 120 and 140 parts per million, and this signifies that we have an aromatic ring. So that agrees with everything we've seen so far. Moving on to our three final peaks, the farthest downfield that we have is one at 50 parts per million. So this is within that region where we're looking at an sp3 carbon that is bonded to a carbon that is bonded to a heteroatom. And in this case, we know that the heteroatom is oxygen, and we know that it's a double bond. So I've reflected that in the table. This carbon is going to be bonded to our carbonyl carbon. And then we have our final two peaks that are under 40 parts per million. So this is the region where we're looking at sp3 carbons that are bonded to carbons that are not bonded to heteroatoms. However, I will say the peak at 35 parts per million is really close to that 40 parts per million threshold. So I'm going to leave the possibility that this carbon is also bonded to the carbonyl carbon as a maybe. And finally, we'll look at our 1H NMR spectra to really get a good grasp of the structure of this molecule. So again, I'll just start downfield and move to the right. We first have a very characteristic peak here. We have a multiplet with an integration of 5H. So when you see one of these at this shift of 7.2 parts per million, this is going to mean that there is an aromatic ring. So again, this is agreed with everything that we've seen so far. Our next peak is sort of interesting. We have a singlet peak with an integration of 2H, so that means we have two hydrogens that do not have any neighboring hydrogens. So what I've written in the interpretation here, as you can see, this is going to be a CH2 carbon. So we have an sp3 carbon that is probably bonded to our carbonyl carbon, which we know there's at least one carbon that is bonded to the carbonyl carbon. But then on the other side, it's also bonded to another carbon that doesn't have any neighboring hydrogens. We can kind of play around with the structures to make sure we can get that to work. Our next peak at about 2.5 parts per million also has an integration of 2H, but it is a quartet, which means it has three neighboring hydrogens. So if we remember from our 13C NMR, I kind of left open the possibility that we would have two carbons bonded to the carbonyl carbon. And this is going to corroborate that because on one side, this CH2 carbon will be bonded to a CH3 carbon, which gives us those three neighboring hydrogens. But we only have three neighboring hydrogens. So on the other side, I'm going to assume that it's bonded to the carbonyl carbon. And then finally, we have our last peak at about 1 parts per million. That is an integration of 3H and is a triplet. So this will kind of wrap it up. This is the CH3 carbon that was referenced on the previous line of the table that has the two neighboring hydrogens of the CH2 carbon that it's bonded to. So if we look at everything that we have seen across all three of our spectra, as well as the sites of unsaturation, what can we tell about this molecule? First of all, we know it's a ketone that has an aromatic ring somewhere in it. We know there is a single or one CO double bond, and then our final three carbons are two of them are CH2. They have two hydrogens bonded to them. And then our final carbon is a CH3 carbon that has three hydrogens bonded to it. Furthermore, the two CH2 carbons, we know that they are bonded to the carbonyl carbon in the CO double bond, which also means that they are not next to each other. If they were next to each other, we would see a lot more splitting because all of these carbons would have more neighboring hydrogens. So we know that they're kind of on opposite sides of the carbonyl carbon here. So let's draw this out to kind of illustrate everything that we've seen. So we'll start with the aromatic ring. That's easy. And then we'll add a single bond here. All of the other points on the ring are going to count up to 5. So we have our 5 hydrogens, which explains the integration we saw on our 1H NMR. So that checks out there. In terms of what carbon is going to go at the end of the single bond, we kind of have two choices. It could either be an sp3CH2 carbon, or it could be our carbonyl carbon. But like I mentioned on our last slide of the presentation, we not only know that the CH2 carbons cannot be next to each other, they're also on opposite sides of the carbonyl carbon. So this carbon right here is going to be one of our sp3 carbons, and then the next one will be our carbonyl carbon. So I am just going to draw this here so that the double bond can be vertical. All right. So here we have our carbonyl, and then we have our CH2 carbon right here. And then on the other side of the carbonyl, we have two more carbons left. We have one CH2 carbon, and oh no, accidentally did an oxygen there. This should actually be a single bond out to our sp3CH3 carbon. So let's kind of check this structure with our molecular formula and check it with some of the assumptions that we made based on our spectra and our sites of unsaturation. So checking the molecular formula first, we're supposed to have 10 carbons, so we have 6 in our phenyl group, and then we have 7, 8, 9, 10. So that checks out. In terms of hydrogens, we're supposed to have 12, so we'll have 5 in our phenyl group. Then we have 6, 7, 8, 9, 10, 11, 12. So that's great. That checks out. And then obviously we have our one oxygen. So the molecular formula is correct. So if we kind of compare to what we had on our last slide of the presentation, this is a ketone. It has a carbonyl with two carbon groups on either side. It has an aromatic ring. It has two CH2 carbons. It has one CH3 carbon. Um, and then in terms of neighboring hydrogens, for the CH2 and CH3 carbons, we can see that this CH2 that's between the phenyl group and the carbonyl carbon does not have any neighboring hydrogens, so that does explain that singlet peak that we saw. Moving on to our next CH2 carbon, its only neighboring hydrogens are the CH3 carbon that is bonded to it, which explains our quartet peak. And finally, with our CH3 carbon, it has two neighboring hydrogens, which explains the triplet peak. So everything checks out compared to what we've seen on our spectra. So we can identify the structure as one phenyl, two butanone. And that is it. Thanks, everyone.